Hey there everybody, Mr. Marek here. In this video we are going to discuss electric fields at the level that you need to know for AP Physics 2. Before we get into anything new, let's review some stuff from AP Physics 1, which is the gravitational field. Remember that objects with gravitational mass, which is basically all objects, cause a gravitational field around them. And a field is simply a disturbance in the space surrounding the object. The bigger the mass, the bigger the disturbance, the bigger the field. Gravitational fields always point towards the object that causes them. So the gravitational field around the Earth could be represented by lines or arrows pointing towards the center of the Earth. And then the magnitude of the gravitational field is proportional to 1 over r squared. That was Newton's famous inverse squared law. And so last year we had an equation that looked like this, where we could find the size of a gravitational field using the mass of the source, the distance to the source, and then capital G is the universal gravitational constant. Remember that G is very, 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 very small, so gravitational forces are very, very, very small. So to kind of put it in another light, mass is what causes a gravitational field. So the mass is the cause, the gravitational field is the effect. On Earth, the surface of the Earth rather, the gravitational field has a value of 9.8 newtons per kilogram. We always use that same value, mainly because our distance from the Earth isn't changing. We're pretty much stuck on its surface. So electric fields are caused by objects with electric charge. So objects with mass cause gravitational fields. Objects with charge cause electric fields. Recall from last year that there are two kinds of charge, positive and negative, named by a guy named Benjamin Franklin. You may have heard of him. Electric fields point away from positive charges and towards negative charges. And so with gravitation, we had one rule: gravity is always attractive. With electric fields, we have two rules. Positive charges cause electric fields that point away from them. Negative charges create electric fields that point towards them. To kind of draw an analogy, you can think of a positive charge as being the top of a hill, an electrical hill, if you will, and a negative charge as being the bottom of the hill. We can write similar relationships for the magnitude of the electric field. Just like the gravitational field was proportional to the mass, the electric field is proportional to the charge. Just like the gravitational field is proportional to a universal constant, the electric field is proportional to a universal constant. And we actually saw this constant last year. It's called the Coulomb's law constant, and we give it the symbol K, and it's got a value of 9 times 10 to the 9th Newton times meter squared per Coulomb squared. Just like the gravitational field, the electric field is proportional to 1 over r squared. It obeys a inverse squared law. And so we can write an equation that looks something like that, where instead of a G we write a K, instead of an M we write a Q, still over r squared. That gives us the electric field. Similarly, the charge is the cause, the electric field is the effect. Now real quick, we kind of need to understand a little bit deeper what this Coulomb's law constant is. Basically, it is a special case of something called the vacuum permittivity, and that is simply a measurement of how well space is distorted by electric fields. The vacuum permittivity is given the symbol epsilon naught, and it's got a value of 8.85 times 10 to the negative 12 Coulomb squared per Newton times meter squared. The two constants are related through this relationship right here. The Coulomb's law constant is 1 over 4 pi epsilon naught. On your formula chart, the equation for the electric field is actually written something like this. What I need you guys to understand is that the 1 over 4 pi epsilon naught is simply equal to K, and you can use the value of K that we learned last year in its place. You just have to know that. The other thing to notice is that it's written in absolute value brackets because the equation simply tells you the magnitude. It doesn't tell you anything about the direction of the electric force. The direction we have to determine using these rules back here. So let's work a real quick example together. Suppose that we have a sphere on which 40 microcoulombs of positive charge is placed. We want to figure out the electric field at point A, which is 0.2 meters to the right of the sphere. So finding the magnitude is simply a matter of substituting into the equation for the electric field. K has a value of 9 times 10 to the 9th newtons times meters squared per coulomb squared. If you don't remember what a micro represents, it's times 10 to the negative 6, which is a pretty common value, like size for a charge, microcoulombs. If you forget that, that's on your formula chart, of course. And then point A is 0.2 meters away. Don't forget the squared in that equation. And we would get a value, magnitude of 9 times 10 to the 6. Investigating the units, the meters squared would cancel out. One of the coulombs would cancel out in the K constant with the coulombs of the charge, leaving us with a Newton per coulomb. And that might tell you a little bit about what the next step is going to look like, going from the electric field to the electric force. And then positive charges cause an electric field going away from them, so the electric field in this situation is going to be to the right. If we were to go the same distance on the other side of the charge, we'd have the same size electric field, it would just point in the opposite direction. So suppose that we have multiple charges. Since charges are really, really small, it is very common for us to have many charges in a given region, and we might want to know things about the electric field surrounding a bunch of charges, a system of charges, if you will. So just like forces, the electric field is a vector. And so we do all the same things that we did last year. Two electric fields are in the same direction, we would add them together. If they're in opposite directions, we would subtract them. If they're not parallel, we would do one of those vector diagrams, add them tip to tail, and use our right triangle trigonometry to figure out the resultant. And so just like we started out with forces last year, electric fields obey the same vector rules that we learned. So suppose we have two charges in an arrangement like this. We want to know the electric field at point A in this situation. And so just for simplicity, I'm going to call the one on the left Q1 and the one on the top Q2. Notice that they have the same magnitude, but Q2 is negative. We can find the size of the electric field at point A simply by doing the vector addition, the vector sum of E1 plus E2. E1 is going to point to the right, and it's got the same size as what we just calculated. Because it's the same charge, it's the same distance away, so I don't have to redo the work of finding the size of E1. E2 is going to point up, because a negative charge would cause an electric field pointing towards it. And we can find the size of E2 just by doing KQ over R squared again. So again, it's the same size charge, we're just closer in this situation. Notice that I didn't put in the negative sign with the charge because the equation only tells me the magnitude. So we're only going to put in the size, not the sign. And that gives me a magnitude of the electric field of 36 times 10 to the 6 newtons per coulomb. So notice that being half as close in distance gave us an electric field 4 times the size. That's that R squared thing showing up. So if we draw a vector diagram, tip to tail, it would look like that. My resultant is going to point up and to the right, and there's two important features, the size and the direction. The size I can find by using Pythagorean's theorem. It's like E squared equals E1 squared plus E2 squared. And that would give me something like 37 times 10 to the 6 newtons per coulomb. So that blue arrow is really a lot smaller than that red arrow. I could write it properly in scientific notation as 3.7 times 10 to the 7 newtons per coulomb if you just really wanted to. And I could use a tangent function to figure out what the angle is. Just do the inverse tangent. And this angle is going to end up being pretty big, something like 76 degrees, because again, the red side of that triangle is way bigger than the right side, or blue side, of that triangle. And so both pieces of information will be part of my answer. Not only the magnitude, but also the direction. And you might write that direction as being up from the x-axis or something to that effect. Electric field lines are vectors which show the direction of the electric field surrounding a system of charges. And so the example that I've got drawn on there, charges would experience electric fields going away from a positive charge towards a negative charge. So what those electric field lines are going to allow us to do is visualize what a positive charge, or how a positive charge would move if we were to let it loose in an electric field. And so around a system of charges, the electric field lines are really helpful for visualizing what exactly is going on. The last thing to discuss is the idea of a capacitor. A capacitor is a device that consists of two parallel plates, like conducting plates. Aluminum pie pans would work as a capacitor, each of area A separated by distance d. When you connect them to a source of electric potential, like a battery, you're going to get charges that collect on the plates, which create an electric field between the plates. And there's something special about this electric field. A capacitor is a good way to store electric charge. If you have a camera that's got a flash that takes a little bit to quote-unquote charge up, basically what's happening is a capacitor is being charged, which can store the charge temporarily and then release it all at once. We'll look at that aspect more of capacitors when we get to capacitors in an electric circuit. So here's the basic picture of what a capacitor looks like. You have one plate on the left that you connect to the positive end of the battery, and then a plate on the right that you can connect to the negative end. When you actually make the connections to the battery, a bunch of positive charges are going to pile up on the plate connected to the positive end of the battery. We could get that charge symbol capital Q, and then the same amount of negative charge is going to collect on the opposite plate. And what that's going to do is it's going to create an electric field in between the plates. The cool thing about the electric field is that it is uniform, meaning it's the same everywhere. And so it's not going to get stronger or weaker as you move in between the plates. The magnitude of the electric field is going to stay constant. And since electric fields go from positive to negative, it's always going to point in the same direction, in this case to the right. I'm not going to go through the process of proving that because it relies on calculus. We just need to know that in between the plates of a capacitor, we get a uniform or same electric field. Now at the edges, the electric field is going to curve out just a little bit. If you kind of zoom in, on this point right here, the charge, if you imagine a charge being there, is much closer to the positive end, and so the positive has a much bigger effect at that point. Similarly over here, the negative charges have a much bigger effect. And that's why at the edges it kind of curves out just a little bit. In between, the vertical forces or fields kind of balance each other, leaving you with the field in one direction. So you just need to know that it kind of curves out just a little bit at the edges. So there's some useful equations for relating the electric field to the voltage that you put on a capacitor. The first is simply a term referred to as the capacitance. The capacitance depends simply on the dimensions of the capacitor, and it looks something like this. And so that epsilon naught constant shows up there. The A is the area of the plates, and then the D is the spacing between them. Typically, these values are going to be extremely small, especially since we do all this in meters. And so you might expect D to be measured in millimeters or tenths of a meter, and area to be measured in very small numbers if we're looking at areas in meters squared. So don't be surprised when those numbers are very small. And we'll look at the unit for capacitance here in just a second. We can use the capacitance to measure the ability of a capacitor to store charge. And so the charge stored on a capacitor is simply its capacitance times the voltage difference between the plates. The capacitance is something that depends on how the capacitor is built. So when you go to the capacitor store and you buy a capacitor, it's always going to have the same capacitance, and it'll typically be stamped on the capacitor somewhere. And so simply multiplying the capacitance by the voltage you put on it tells you how much charge is placed on the edges of on the plates of the capacitor. And then the electric field on a capacitor, we can simply use the difference in voltage over the spacing between them. That would give us the electric field between the capacitor. So these equations are probably going to make more sense when we put them in the context of an example. So suppose we have two plates that are connected, or separated rather, by a distance of 4 times 10 to the negative third meters. It's actually a pretty big distance. And have an area of 2 times 10 to the fifth meters squared, which is a reasonable area considering that a meter squared is very large. We want to figure out the capacitance, the charge on the plates, and the electric field between the plates. So the capacitance is basically a substitute and evaluate kind of thing. And so epsilon naught times area over D. Epsilon naught, again, has a value of 8.85 times 10 to the negative 12 coulomb square per Newton times meter square. The area is 2 times 10 to the negative fifth meter squared, and the distance separating the plates is 4 times 10 to the negative third meters. So multiplying those numbers together is relatively straightforward. You get a number that looks like that. The key to focus in on here is the unit. On the right-hand side of our substitution, the meter squared and the meter on bottom will cancel out. And then the other meter on top will cancel out with one of the meters in the epsilon naught term. And so what we're left with is something that looks like that. Coulomb squared over Newton times meter. Remember that a Newton times a meter is a joule. And so the unit for capacitance is Coulomb squared per joule. And that's typically referred to as a farad, named after Michael Faraday, who we're going to learn a lot about later on. He was a British scientist that did a lot to develop the science of electricity and magnetism. He's going to become way more important to you guys later. For right now, just realize the unit for capacitance is called a farad, which is given the symbol F for short. And so very, very small values in farads for capacitance is to be expected because the meter squared, again, is a very large unit of area. To figure out the charge on one of the plates, simply take that value and multiply it by the 12 volts. Remember that volts is a joule per coulomb. And so just substitute in joules per coulomb instead of volts, and you'll see how the joules cancel out. One of the coulombs cancels out, giving us a charge of 5.3 times 10 to the negative 13, and then the unit is coulomb, just as we would expect for the charge. Find the electric field, we can just substitute into that equation, delta V over delta D. So divide the 12 volts by the distance separating the plates, and we get a relatively large value, compared to the other things we're dealing with, of 3,000 for the electric field, and the unit is volt per meter. So remember again that a volt is a joule per coulomb, and then divide that by a meter. If we kind of do some rearranging of what a joule is, Newton times a meter, so a joule over a meter would be the same as a Newton. So that part right there is a Newton. So that gives us an electric field of 3,000 Newton per coulombs, just like all the other electric fields that we have looked at so far today. So the unit joule per coulomb and the unit volt per meter are actually the same thing. They can be used interchangeably. So if you were to just write down 3,000 volts per meter, that would be perfectly okay. So before we get to class next time, here are the 3 big things that we need to be able to do. You need to be able to figure out the magnitude and direction of electric field around a single charge or a system of charges, and then find the magnitude and direction of the electric field in between the plates of a capacitor. We also want to be able to find the actual capacitance and then use that to figure out how much charge is there and then kind of relate all of it. So class next time is basically going to be spent trying to make sense of all these menagerie of equations and try to put some physical meaning to some of these things. Right now, the value of 4.4 times 10 to the negative 14th farads probably doesn't mean a whole much to you. We'll spend class time trying to make some meaning out of it. And then the next time we meet together via the magic of internet video, we're going to discuss what happens when you actually take an electric charge and put it in an electric field. Here's a hint. It's going to look a lot like putting a mass in a gravitational field. Till then, ta-ta.